example, the picture. Let me see. Can I? Can you see what I'm drawing? Hello?
Nope, we don't see.
You're not able to see? Okay.
Do you use the dashboard, Professor?
Yeah, I am actually using, okay, just a minute. Okay, I see. I know that's why. Let me. Okay, can you see now?
Yeah.
Okay, can you see what
Yeah,
I'm drawing?
we see a circle.
Okay, good. Okay, good. So we have A and this is V minus A, right? Okay, and remember, so all the cross edges are connecting the vertex, right? All these are, this is a cross edge, right? Connecting a vertex U to a vertex called V, right? Okay, so this vertex, this edge connects the vertex U to a vertex V, right? Okay, so let's say V is a vertex in V minus A, capital V minus A. And this V has a lot of cross edges, right? Okay, a lot of cross edges, right? So among all these cross edges incident to V, we choose the one with the lightest edge weight, okay? Okay, so let's say this is 5, and this is 7, this is 2, and this is 10, and this is 13, right? So 2 will be the smallest. So the key for this vertex V, okay, is equal to 2, right? So remember, all the vertices in V minus A are inserted into the priority queue, okay? Inserted into the priority queue. The key of every vertex, okay, is the lightest edge weight of the cross edges incident to it, okay? So in this example, 2 would be the key for this vertex 2, okay? So every time in this Prim's algorithm, right, in this while loop, okay, we do extract min. So extract min is going to go to this V minus A and extract the vertex with the smallest key, which is what? The smallest edge weight, okay? So we're going to extract that vertex, okay? And that's called U, okay? So that's U, right? And then, so this U, okay, this U will be the vertex that will be added into the A side, okay? A is the minimal spanning tree that we're growing, okay? Minimal spanning tree that we're growing. And B minus A has all the vertices that are not yet spanned in the minimal spanning tree that we're growing, right? A has all the vertices, that are already spanned in the minimum spanning tree that we're growing, okay? So when you extract mean, and that's called this U, then U will be added into A, meaning we're going to use the edge. We're going to use the edge that whose edge weight is the representative cross edge, okay, which is the key of U, okay? We're going to use that edge, okay, and add that into the minimum spanning tree, right? So the extract min is going to extract vertex, okay, and add it into A. And then what we need to do next is to do update, okay? What I mean is this. Let's say V is the vertex, okay? So I'm sorry, let's call this U, okay? So this is U, okay? And then now U got extracted, okay, as the smallest vertex, right? Whose key is the smallest, meaning the cross edge incident to U is the smallest among all the cross edges. And okay, and then for all the neighbors of U, okay, if V is still in the priority queue, okay, meaning what? Meaning this, let's say, okay, if I have this neighbor, sorry. Okay, all right, so this is U and this is V, okay? So now U is going to be pulled over to A now, right? After the extract min, okay? So for this neighbor V, okay, after we pull U from B minus I to A, this edge will become a new cross edge, right? Will become a new cross edge. So we're going to examine if the edge weight, is smaller than the current key of this vertex V, okay? If it is smaller, then we need to update the key of this V, okay, to be the edge weight of this new cross edge, right? Okay, and set this the predecessor of V to be U, okay? So, and then we do this for every vertex of U, okay? That is still in B minus A, okay? We do this, okay? And then, so every vertex that we extract from the priority queue, we add it into A until the entire priority queue is empty, okay? Until the entire priority queue is empty. Then all the vertices are already spanned, okay, by the minimal spanning tree. Okay, so that's how this algorithm works. Okay, all right. So any question on this? Are we good? Okay, then we're going to move on. All right. So and we went through this as an example, right? Last week. Remember, this is the vertex that we arbitrarily picked, right? And we added into A, right? Okay. Okay. So okay. So then this vertex, okay, becomes added into A, right? So all the red nodes are in the priority queue right now, okay? And the number in the circle is the key, okay, of the vertex in the priority queue, okay? They are all infinity, okay? All right, and then now because we add this vertex, okay, because we add this vertex into A, therefore you see I have 3 edges becomes cross edges, right? Okay, the one with 7, the one with weight 15, and the one with weight 10, right? So all these becomes cross edges, okay? And this vertex, okay, will have the key equal to 7 because this is the only cross edge, right, incident to this vertex. Same thing for this guy, right? Same thing for this guy. The key will become 15, and this guy will be 10, right? So after that, okay. So you see all the 3 vertices, okay, have the updated key, right? So the top is 7, the left is 10, the right is 15, right? Simply because those 3 pink edges become cross edges, right? Cross edges between A and B minus A, right? And then the extract min will extract among all the red vertices, the one with the smallest key, which is 7, right? And add that into the minimum spanning tree that we're going. Okay, so 7 will be added into it. Okay, now 7 is in A now, right? So this decision changes this edge to be cross edges, changes this edge to be cross edges, and changes this edge to be cross edge, right? So the corresponding vertices will also have the updated key, right? So you see, right? So this vertex becomes to have key equal to 9, and this has key equal to 12, and this has key equal to 5, right? Okay. Now you have these remaining 6 vertices in the priority queue again, right? In the next iteration, we're going to pick the one with the smallest key, which is 5, right? Okay. So 5 will be added into A, right? And then now again, so this edge will become new cross edge, and this edge will become new cross edge, right? So we update the corresponding vertex key, right? Okay, so you see this becomes 6 and 14, right? And then next you pick 6, okay, to add into the party queue, right? And no new cross edges. Therefore, there's no vertex key update, okay? And next you choose 8, right? Okay, so sorry, somehow this, okay, so you choose 8, okay? And there is this new edge becomes cross edge. So this key will need to be updated because this becomes the smallest cross edge incident to it, right? So between 3 and 14, 3 is the smallest. Therefore, this the key of this vertex will need to be updated to be 3, right? Okay, and next select extract mean, we'll choose this, okay? And no new cross edges, right? And next one you would choose 9, no new cross edges, and next one you choose 15, right? Okay, so this, you see all the pink edges are the 3 edges of the final minimum spanning tree, okay? All right, so that's and how the entire algorithm works. Okay, and we're going to do the analysis. Okay, the analysis, we start with the very first one, which is to build a party queue. Okay, all right, and then we add all the keys, right? So when we add into the party queue, right, every vertex has a key, right? So these are the assignment. Only one of them that we randomly pick will get 0. The remaining will be infinity. They are all got, they are all inserted into the parity queue. Okay, and then we do this iteration. Okay, so so you see the initialization takes order of V. Okay, and then uh, and then the next one, okay, is to do this while loop. In this while loop, you see the priority queue has total number of vertices, and you're going to extract one at a time. Right? So totally you're going to do this iteration V amount of times. Okay, and so extract mean will get called V times. Okay, and then for this loop, right? For every vertex that got extracted, you're going to look at the neighbor and compare the edge weight with the current key and so on. Okay, so for every neighbor, you're going to do this comparison and do the assignment and update, right? Okay, so you see this entire number of neighbors that you have to look at. Every vertex, you're going to look at all the neighbors. Therefore, you're going to execute this for loop. Okay, the number of times equal to the degree of u, right? The number of edges incident to u. Okay, so this iteration will run degree of u amount of times, right? Okay, and you're going to run this entire thing, right? The entire while loop for every vertex. Therefore, the number of times that you're going to execute this innermost for loop, right? This innermost for loop is equal to what? Is equal to summation of degrees among all the vertices, which is equal to what? Summation of all the degrees of the vertices is equal to 2 times the number of edges, right? You remember that? Okay, the summation of all the degrees, okay, of all the vertices is equal to 2 times the number of edges, right? It's due to the very famous lemma called handshaking, right? We talked about that last week, right? Okay, so the total number of time that you're going to execute this for loop is equal to number of e, right? And the key operation is this operation. This operation is called decrease key, right? You're going to decrease the key of a vertex in the priority queue, right? Okay, so the number of time to call decrease key is order of e, and the number of times to call extract mean is equal to number of vertices. Therefore, the total amount of time is v times the amount of time to run extract mean plus e times the amount of time to run decrease key. Okay, so this is the total amount of time. Okay, to build the minimum spanning tree using Prim's algorithm. Okay, again, is that the number of time to run extract min is equal to v, and the number of time to call decrease key is equal to e. Okay, so v times time to run extract min plus e times time to run decrease key. Okay, that is the total amount of runtime for minimum spanning tree. Okay, all right, so this is going to be our last slide. Okay, so we're going to compare, okay, we're going to compare different implementation of the priority queue, okay, priority queue. Okay, we're going to look at 3 different ways to implement priority queue, and their corresponding Prim's algorithm runtime, okay, will be also shown here. Okay, the first one is, suppose we use the linear array to implement priority queue. Okay, extract min to find the minimum element in the linear array takes how much time? Linear time, right? Okay, so that's order of v. Okay, and decrease key, you just decrease the key of the corresponding element, so that's constant time. Okay, there's no other time spent on this. Okay, so v times v plus e times 1, right? So that's v squared plus e, right? And remember, e is bounded by v squared, so the total time for this is equal to v squared for linear array. Okay, now the second data structure we're going to use to implement priority queue is called binary heap, right? We all learned about this, right? This is min heap, right? Okay, so the final exam is next week, right? Okay, so I hope everybody has already started preparing for it. So for min heap, right? Extract min takes log of v, right? Okay, log n, right? This n is equal to the number of elements in the priority queue, which is equal to the number of vertices, right? Remember, the priority queue stores all the vertices at the beginning, and we extract one at a time, right? Okay, so the extract min takes log of n, log of v, and the decrease key takes log of v. Again, you decrease. When you decrease the key, right? You decrease the key, you could very likely violate the min heap property, right? If your key, right, is smaller than the parent, right? If your key is smaller than the parent, right, then you violate the priority queue, the min heap property, because the min heap property says that the parent has to be smaller than or equal to the children, right? So if you decrease the key to the extent that you are smaller than your parent, okay, then you need to fix it, right? So how do you fix it? You should not say heapify. Heapify will not work, right? Remember? Okay, so this one we should actually compare flow up. Okay, you should actually compare up to you do decrease key, right? So you should actually compare with the parent, and you should float. You should float the vertex that you are decreasing the key up, okay, to the point that the parent is smaller than it. Then you stop, right? So the worst case is order of n, which is the worst case is log n, right, which is the height of the min heap. Okay. And then, so the total is v times log v plus e times log v. Okay, so it's dominated by e times log v. So this is the total runtime. Okay, now Fibonacci heap is not something that you have learned. Okay, so this, if you take 680, okay, next trimester in 680, I'm teaching it, then you will be able to learn this. Okay, this data structure actually supports log n. Okay, log n for the extract min, and actually constant, you see, constant for decrease key. Okay, so that's a big improvement there. Okay, so the total is v log v plus e times constant, therefore is e plus v log v. Okay, so this e plus v log v, as you can tell, that the Fibonacci heap implementation is better than both of them. Okay. So and it turns out that the Prim's algorithm runtime, okay, is exactly the same as the Dijkstra algorithm, finding the shortest path algorithm, right? So this is finding the shortest path algorithm is also the important topic we're going to cover in the 680. Okay, so I look forward to seeing all of you in 680. Okay. All right, now so minimum spanning tree. This is the last slide. Okay, so other than Prim's algorithm, there's another very famous algorithm called CrossGoes. Okay, CrossGoes. Okay, CrossGoes algorithm. Okay, say very carefully. CrossGoes, not Costco. Okay, CrossGoes algorithm. Okay, so this CrossGoes algorithm, it runs. The algorithm is different than Prim's algorithm. It actually sorts all the edges. Okay, in the increasing order. Okay, and it starts adding the edges one at a time into the minimum spanning tree. Okay, you start with the one with the minimum edge weight. Okay, so and then you add the next one, and then you add the next one. Whenever you detect a cycle, okay, then you drop it, because minimum spanning tree is a tree. Okay, it should not have a cycle. Okay, so you got a sorted increasing order edges. Okay, in edge weights, right? And then you start adding one at a time. And whenever you see a cycle, you discard the edge, and you keep on doing it until all the vertices are already spanned. Okay, and this particular algorithm can be implemented using the so-called disjoint set data structure. This is covered in chapter 21, and we will also cover this data structure in 680. Okay, it's lecture number 4 that we're going to cover that. So the runtime for CrossGoes algorithm is dominated by what? It's dominated by sorting the edges. Okay, sorting the edges, right? How many edges are there? E, right? Okay, E is the number of edges. So sorting them is E log E, right? Remember, right? Sorting algorithm, the best sorting algorithm is N log N, right? So it's E log E, right? Now E is at most V squared, right? So log V squared is equal to 2 times log V, right? Remember, log V squared. Okay, you bring the 2 down, right? Okay, so what I'm saying is log V squared, right? Okay, you is equal to 2. You bring this 2 down, right? 2 times log V. Okay, so this is equal to log E, right? Log E is upper bounded by log V squared. Log V squared is equal to 2 times log V. So E times log E is exactly E times log V, okay? Right? So E times log V, okay? So that's the runtime of CrossGoes algorithm, okay? All right, so that's the second famous algorithm for the finding the minimum spanning tree. Okay, one is Prim's algorithm, the other is CrossGoes algorithm. All right, so the best algorithm that we know, okay, for finding the minimum spanning tree was published in '93. Okay, it's a randomized algorithm. Okay, and the expected runtime is actually V plus E. So this is very fast. Okay, it's linear. Okay, but it's expected runtime. This is not the worst case. Okay, expected runtime. You know the difference already, right? We talked about the expected runtime for quick sort, for the randomized select, and so on, right? Okay, so okay, any question? This is it for the greedy algorithm. Okay, so we're going to move on to talk about the next. Any question? Okay, I plan to finish this lecture in another hour. Okay, so by your 8 o'clock. Okay, I am right now in China, so this is 11 a.m. right now. But I will finish the next topic in an hour. Okay, so this topic is about NP completeness. Okay, so NP complete. Can you see the slides?
Yes, we can.
Okay, good. Yeah, this Zoom is amazingly good, right? It's so clear. Sako, I can hear your voice very clearly. Can you guys hear me very well?
Yeah, the quality is really nice.
Okay, okay. Are you able to follow through what I said?
Yeah,
Okay, I was actually repeating what I taught last week, right? Except the last two slides, which I couldn't cover at the end because you guys need to go home, right? So okay, so now this is the last lecture of 580. Okay, it's about NP completeness. I don't expect your when you go to job interview. I don't expect your interviewer will be able to ask a question related to NP completeness because this is rather theoretical. However, this is a very very good knowledge to have. Okay, because when you know about NP completeness and you explain to other people about NP completeness, they all feel that you are the man. Okay, you are the lady. Okay, they all feel that you are so knowledgeable and so on. Okay, because this is a theoretical topic. However, it also means a lot in practice. Okay, let me quickly go through some fundamental concept. Okay, okay. So now that's we have to spend so much time in this trimester talking about those problems that are polynomial time solvable, right? We talk about sorting, we talk about searching, right? And then we talk about the all the data structures, right? The binary search tree, the red-black tree, and so on. And then we talk about the dynamic programming, right? I kept emphasizing that when you do the dynamic programming, you have to make sure that your formulation is able to produce a polynomial time algorithm, not the exponential time, right? And then we just finished the greedy algorithm. We used the minimum spanning tree example to demonstrate to you that with greedy heuristic greedy algorithm in it, you can solve the minimum spanning tree problem optimally, right? In this v log v plus e time, right? So all of these are polynomial time solvable problem. Okay. Now, then the very natural question is that what about other problems, right? Okay. So this picture show you some kind of hierarchy, okay, of the difficult problems. Okay. So the inner circle represents the polynomial time solvable problem. Okay. Now the bigger circle containing it, okay, are those problems that are solvable, okay, that are solvable using exponential amount of time, okay, and then the next bigger oval, okay, represent is the doubly exponential time solvable, okay. So a doubly exponential is meaning what? Doubly exponential means what? Okay, means like 2 to the 2 to the n. Okay, 2 to the 2 to the n, right? This is doubly exponential, right? If your algorithm needs this, okay, can you tell that this is different? Can you tell this is different from 2 to the 2 to the n, right? Okay, these are different, right? Okay, the right-hand side, 2 to the 2 to the n, this is equal to 4 to the n, right? Okay, now 2 to the 2 to the n, okay, is much bigger than 4 to the n. Okay, so these are two different things, okay? This is just a sidetrack, okay? So you see, doubly exponential amount of time problem is a much bigger set, right, than the exponential time solvable, okay? All right, and then the next oval is in blue, right? Those problems that need even more than exponential, doubly exponential. Okay. Now even beyond those that more than doubly exponential. Okay. We actually have some problems that are actually unsolvable. Okay. They are actually unsolvable using the computer. Okay. So the unsolvable problem. Okay, so one example of unsolvable problem is that just for your knowledge as an example. Okay, is that I suppose I give you an algorithm. Okay, I give you an algorithm. How can you decide if this algorithm will actually terminate? Okay, given an algorithm, how do you decide if this algorithm will terminate? Okay, that problem is actually an unsolvable problem. Okay, as an example. Okay, so if you want to understand why and so on, right, there's a course taught by Professor Richard Reel. So this is the kind of knowledge that can be covered in that course. Okay, I don't know whether he covers that or not, but this is something that can be covered there. Okay, so this picture gives you some idea. Okay? Gives you some idea of the hierarchy of the problems that we're solving. Okay. Now the next one is that if you think about the problems we have considered so far, right? Okay. For instance, the uh, the optimization problem, right? Such as the finding the longest common subsequence, right? LCS, right? And also finding a minimum spanning tree, right? And so on. Okay. So we can always uh, convert or translate. We can actually convert these problems to be the so-called decision problems. Okay, to be a decision problem. Okay, and the decision problem actually is a problem that is asking you to give an answer as yes or no. Okay, that's why it's called decision problem. Okay, for instance, okay, given n line segment, line segment, okay, do they have an intersection or not? Okay, that's a decision problem. Okay, or the next example. Okay, Super Mario Brothers, right? This is the video game, right? Okay, the level. Okay, you know, there are many levels in this video game, right? Is there a solution or not? Is there a solution that you can go through this level by level and go all the way in this video game? Okay, or you know this Rubik cube, right? This Rubik cube that you're playing in your hand, right? In your hands, you make sure all the six sides have the same color, right? So, a decision problem is this: does the Rubik cube problem always have a solution in 20 moves? Okay, is it yes or no? Okay, or what? Or the next, given a sequence of a poker cards, right? Is there a crazy eight subsequence trick of at least 17 cards? Okay, I'm not good at the poker card playing cards, so I don't exactly know what this crazy eight game is, so I cannot elaborate on that. Now the last one is: does a given weighted graph have a negative cycle, right? It's yes or no, right? A weighted graph has a cycle whose length is equal to a negative number, right? So these are the decision problems, okay? And it turns out that the optimization problem, right, when you're trying to minimize or optimize, those are the optimization problem, right? The optimization problem, okay, versus the decision problem, okay? You will feel that, oh, decision problem in some sense is easier, okay? Because you only need to say yes or no. Whereas optimization, you need to find the smallest, you need to find the largest, and so on, right? These are optimization problems. So you got, in some sense, the decision problem is easier, okay? Or at least no harder than the optimization problem, okay? So here's an example, okay? Shortest path problem. Shortest path problem, okay? Shortest path problem is that a graph, I give you a graph, right? Okay, and the vertex u and b. I give you a graph, directed graph G, and vertex u and b. Okay, and I give you a integer k. Okay, I ask you, okay, in G, can you find a path from u to v? Okay, such that this path has at most k edges. Okay, So this is the so-called path problem. It's a decision problem, right? The answer is yes or no, right? Right? Does a path exist? Okay. Okay. Does I should not say can you find, because that depends on the each person's capability, right? This is asking a fact. Okay, is asking a fact in a graph and the UV in the graph and the integer k. Does this graph have a path from U to V such that this path has at most k edges? This is yes or no question, right? It's a decision problem. And we can solve this decision problem. We can solve this decision problem by solving the optimization problem, right? If we can find the shortest path from U to V, right? Okay, then we just find it. We just find the shortest path, right? And take that number of edges in that shortest path and compare with k, right? If that short number of edges in the shortest path is smaller than k, the answer is yes. Smaller than or equal to k, then the answer is yes. If that number of edges in the shortest path is greater than k, the answer is no. Okay, so then you see that if we can solve the optimization problem, right? We can solve the optimization problem, then we can solve the decision problem easy, right? Okay, you just solve the optimization problem and then answer the decision problem easily, right? Okay, so this is an evidence that a decision problem, okay, is okay. So this is an argument. Okay, this is an argument. Okay, to tell you that if you can show a decision problem is already very difficult. Okay, is already very difficult. Then the corresponding optimization problem is also difficult, right? So this is obvious, right? Okay, so if you can solve the optimization problem, you can solve decision problem easily. If you can prove that your decision problem is already very difficult, then the optimization problem must be also very difficult, right? Okay, so that's the concept in this. Okay, all right. So that's the difference between decision and the optimization problem. Okay, now we're going to talk about this. Okay, we're going to talk about this terminology called NP. Okay, NP. And this NPN means what? Means non-deterministic. Okay, a lot of people say this N is equal to NOT. No, it's not. It's not. This N is not translated as not polynomial. NP is not. Okay, this is a common mistake. Okay, people say NP is not polynomial. Okay, that's a wrong explanation, wrong definition. NP means non-deterministic polynomial. Okay, non-deterministic. Okay, what does that mean? Non-deterministic meaning that if it is deterministic polynomial, then it's a polynomial time, right? It's a polynomial time solvable. You can deterministically solve the problem, okay, in polynomial time. So that's P. Okay. Now, when we say non-deterministic polynomial, that means what? That means you are actually not going to solve the problem in polynomial. Instead, for these problem, any problem in NP, okay, is a problem that can be verified. Okay, that can be verified if a given solution is a solution in polynomial time. Okay, so NP is a problem. Okay, is a problem that you can find a polynomial time algorithm to verify. Okay, you can find a polynomial time algorithm V. Okay, there exists a polynomial time algorithm V. Okay, this V takes this problem A. Okay, and a solution. Okay, and a solution Y. Okay, solution. This is a problem. This is a problem instance in A, problem instance X in A, and the solution in Y. And this V can run in polynomial time to check whether this y is a solution of x or not, right? If it is, it returns true. If it is not, it returns false. Okay. All right. So uh, okay. So x is a yes input. Remember, this is a decision problem, right? We're talking about decision problem because we said that if we can prove decision problem is hard, right, then the optimization problem is also hard, right? So now, because in this lecture, we're going to talk about hard problem, okay? Therefore, we focus on decision problem, okay? We want to show there are a lot of problems, even in the decision problem level, they're already very difficult, okay? So we'll focus on decision problem, okay? So for decision problem, okay, decision problem A, okay, decision problem A, okay. So let's suppose for problem instance X is a problem instance for A, and the answer to this X is yes, okay, okay, because it's a decision problem, right? So the answer to this instance is X, is yes, okay, is yes. Then there exists a solution y, a guess, okay, that you make a guess. You make a guess y. The length of this y, okay, the length of this y has to be bounded by the length of your problem instance. Polynomial has to be bounded by the polynomial of the length of your problem instance. Okay, and this polynomial time algorithm will take this problem instance, which the answer is yes, okay, and this guess of the solution y, okay, and verify if this y is exact the solution, okay, to give this x the yes answer, okay. And then now if x is a no problem instance, okay, is a no problem instance, meaning this decision problem x instance, okay, has the answer no, okay, then this algorithm v that runs in polynomial time will take x and take all the other guesses of the solution, and it would answer false, okay. Correspondingly, it would answer false, okay. So then this, if such a polynomial time algorithm to validate, okay, to validate a problem, decision problem, okay, and to give a decision problem x and the guess of the solution, and would answer correctly, it can answer correctly, then such a problem is called NP. Okay, it's called NP. Okay, so now you might want me to let me see if I have a example. Okay, so now let's give a quick example. Okay, so let's say given a graph, we want to ask. Okay, given a graph. Okay, that's just instead. Okay, let's use this as an example. Okay, now instead of finding the shortest path, let's say we want to find the longest path. Okay? Given a graph and the vertex u and v, okay, and the integer k, we want to ask in this graph, does a path exist from u to v, okay, that consists of at least k edges, okay, k edges, at least k edges, because we're finding the longest path, okay. So we want this as high as possible, the optimization problem, right? I'm sorry, the decision problem of the longest path is to find at least so many edges, right? Okay. Okay. So this is a decision problem. Now, if I give you a guess, so let's say, okay, let's say this k, okay, let's say this k is equal to 32. I give you a graph, I give you u and v, and k is equal to 32. Okay. Okay. Then I also give you a path from this u to v. Okay. Then you can take this path to check whether this path actually connects from u to v in this graph, and the number of edges is at least equal to k or not, right? So that verification can be done in polynomial time easily, right? That's actually doable in linear time, right? You just scan through this path, right? This path and check if it is indeed a path from u to v, and the number of edges is at least 32, right? You can answer that yes or no, right? So the longest path problem is obviously in NP, okay? Okay, because I give you a problem and I give you a guess. You can easily verify, okay, this guess is a solution to the problem or not in polynomial time, okay? So finding the longest path problem in the graph is in NP, okay? All right, now, and also all the problems, okay? So the question is, how about those problems that are solvable in P? Okay, those problems that are solvable in P. Okay, so all the problems that are solvable in P must be verifiable in polynomial time also, right? Right? Okay, if you can solve the problem, if you can solve the problem in polynomial time, then I give you a guess. I give you a guess of the solution. You can easily verify. Okay, you can easily verify if this guess of the solution is indeed a solution or not. Okay, so P is obviously a subset of NP. Okay, meaning a decision problem that is solvable in polynomial time must be verifiable, in polynomial time. Okay, all right. So P is obviously a subset of NP. Now the question is P a proper subset of NP, or P is equal to NP? Okay, you see, I have a set A, which is a subset of another set B, right? Then there are two possibilities, right? A is indeed a subset of B, right? And another is A is actually equal to B, right? Okay, okay. So when you say is a subset, A is a subset of B, that means A can be either properly contained inside B, or A can be exactly equal to B, right? Okay. So we just realized that P must be in NP because solvable must be verifiable. Okay. But is P equal to NP? That's the question, right? Okay, is it a proper subset or is it equal? Okay, all right. So then equivalently, you're asking, is it easy? Is it easy to solve as to verify? Okay, right? So are they the same thing or not? Okay, right? So solve. Okay, so we know that to verify is easier than to solve. Okay, but is it equally easy? Actually, okay. The question is, that's the question: is P equal to NP? Okay, are they equally difficult or equally easy? Okay, so this question has been open since 1970, and it has been going on for almost 50 years, and nobody in this 50 years, okay, has been able to prove or disprove, does P is equal to NP or not. Okay, so if I test you in the final exam, is P equal to NP? Okay, the correct answer is nobody knows. Okay, okay, Richardson doesn't know either. Okay, nobody knows. Okay, so all right, so nobody knows, right? But there are still a lot of problems, okay, that we don't know, okay, that we that that we that we want to see. Okay, we want to see that if this is an open problem for 50 years, right? So how can we actually? What is the right approach to solve this problem? Okay, what is the right approach to look at this problem and go a little deeper? How can we make progress? Okay, on this P equal to NP problem. Okay, so the very intuitive idea, a very intuitive idea is this. Okay, so we know P is a subset of NP, right? P is a subset of NP. Okay, so let's try to see that if we go to the larger set NP, okay, we go to the larger set NP, and we try to find the hardest problem in NP. Okay, if we can prove that the hardest problem in NP, okay, is not in P, then we prove what? Then we prove P is a proper subset of NP. Get it? Right? If we can prove the hardest problem in NP, okay, hardest problem in NP is actually in P, then we have already proved that P is equal to NP, right? So one way or the other, okay? So the key here is that let's try to bring in the hardest problem in NP and decide on whether these hardest problem in NP are in P or not, right? If we can answer that question, we have solved this problem, okay? All right, so now what are these hardest problem in NP? The hardest problems that are polynomial time verifiable, okay? These problems are called NP-complete problems, okay? All right, so now here's a picture to further explain the concept, okay? So NP-complete is the set of the problem inside NP, okay? NP-complete is a set of problems inside NP, okay? And they are the hardest, the most difficult problems, okay, in NP. Now, if we can prove these problems are not inside P, okay, these problems are not inside P, then we can prove P is a proper subset of NP, right? P is a proper subset of NP because these are not in P, okay? However, if we can prove the hardest problem is also in P, then we have proof P is equal to NP. So the key is to focus on solving the NP complete problem, the hardest problem in NP. Okay. All right. So now we just say that the hardest problem in NP. Okay. So what do we exactly mean? A problem is the hardest problem in NP. Okay. All right. So now I have to bring in this concept called polynomial time reduction. Okay. Polynomial time reduction. Okay. The polynomial time reduction is this. Okay. Polynomial time reduction is the following. Okay. Let's say I have A and B. They are both decision problems. They're both decision problems. And I said that A is polynomial time. A is a polynomial time reducible to B. Okay. A can be reduced to B. Okay. Right? If there exists a polynomial time algorithm R. Okay. Exists a polynomial time algorithm R. This polynomial time algorithm R can transform a problem instance X, okay, X inside A, into a problem instance of B, okay, so that, okay, if X, okay, X problem instance, okay, is a decision problem, right? The answer is yes, okay, if and only if the corresponding transformed problem instance in B is also has a yes answer, okay, and if the X answer to that decision problem is no, then the corresponding problem, okay, transform problem in problem instance in B also has the answer no. Okay, this has to be if and only if. Okay, if such a transformation R exists, okay, this R has to be polynomial time. Okay, R has to be polynomial time. If this polynomial time algorithm R can transform a problem instance from A to a problem instance to B, okay, in B, okay, such that their decision answers are the same, okay, then we call A is polynomial time reducible to B, okay, meaning you can transform any problem instance X in A to a problem instance in B, polynomial time, so that their solution space are preserved, okay, and this is a notation. A is reducible to B in polynomial time, okay, and we can use this picture, okay, we can use this picture to show you, okay, so A is a problem that a problem has many instances, right? Has many instances. Okay. Now the purple area, okay, represent all the problem instances whose answers are yes. Okay. And the yellow area are all the problem instances whose answers to them are no, right? Okay. Then you take this polynomial time reduction from A to B means that there exists a polynomial time algorithm that can transform any problem instance in the purple, inside the purple of A, to a problem instance inside the purple in B, and any problem instance, okay, in yellow, okay, and be transformed in polynomial time to a problem instance in B, also in yellow, okay. If such a polynomial time algorithm transformation exists, okay, then we say A is polynomial time reducible to B, okay. All right, so why do we care about this definition, polynomial time reducible? Okay, because of this very important property. Okay, the property is this. Okay, it says that, okay, if A is polynomial time reducible to B, okay, then if B, okay, if B has a polynomial time algorithm to solve B, okay, problem B can be solved in polynomial time, okay, then problem A can also be solved in polynomial time, okay. Why? Because of very easy proof, okay. Now you see, if we said that if B, okay, A is polynomial time reducible to B, and B is also polynomial time solvable, okay, then we can do this, okay. For you take any problem instance in A, okay, let's go through this transformation because A is polynomial time reducible to B. We go through this transformation R, okay, to a problem instance in B, okay. Now, because we said B is polynomial time solvable, right? So B, it has an algorithm to answer that instance yes or no in polynomial time, right? When that algorithm says yes, then the yes answer is the yes answer for this X instance to A. If that answer says no, then no is the answer for this problem instance X in A as well, okay? So you can combine this polynomial time transformation algorithm, okay, this reduction, and the polynomial time algorithm for B to solve, okay, to solve the problem in A, okay? So that's why, okay, that's why this polynomial time polynomial time reduction is important, okay? Okay, now, so the runtime, okay, in this case, the runtime for A, okay, the runtime for A is equal to the runtime of R, okay, is polynomial time reduction transformation, plus the polynomial runtime to solve the problem instance in B, right? Adding these two together, right? That will be the runtime for A, right? Okay, so this should be quite logical, right? Okay, so so here is that if transformation runs in this P of X, okay, this polynomial of X, right? This problem instance of A, right? And B's algorithm runs the polynomial Q in Y, okay? Okay, then the runtime for the A is P of X, okay, to do the transformation, okay, plus Q of P of X, because after that you have to transform to the input to B, right? So the resultant problem instance to B is P of X, okay, so which is still a polynomial, okay, a polynomial of A, okay. Now the next, okay, the next is the key observation. Okay. All right. So we know that, okay, if A is reducible to B and B is polynomial time solvable, then we know A can also be solved in polynomial time, right? Okay. So there are two uses, okay? One is that if B is polynomial time solvable, then we can use that algorithm to solve A, as you can see in previous slide, right? This is the way to solve A, okay? Now, on the other hand, another way to look at this is this. Another way to look at this is this. If B, okay, if B is already very difficult, okay, if B is already very difficult, okay, then A, okay, would be at least, okay, would be at least as hard, okay. So, okay, I'm sorry. Okay, I say totally wrong. Okay, I'm sorry. So the first one is still right. Okay, so if B is polynomial time solvable, okay, if B is polynomial time solvable, then A is polynomial time solvable, right? So which is exactly what I said previously. Okay. Now the next one. Okay, another way to look at it is this. Another way to look at it is if we say A, if we say A is already difficult. Okay, if we say A is already difficult, then we say B, okay, we say B must be at least as hard as A. Okay, now think about this. Okay, look at this very carefully. All right, so remember the previous slide we said that if B is polynomial solvable, then A is polynomial time solvable, right? Okay, if B is polynomial time solvable, then A is polynomial time solvable, right? Okay, so that means what? That means B, right? The harder problem, if the harder problem is solvable in polynomial time, then the easier problem is also solvable in polynomial time, right? Naturally, right? So B is at least as hard as A. Okay, so there are two ways. There are two ways to look at this polynomial time reduction. The first way to look at it is B is polynomial time solvable, A is also polynomial time solvable. Okay, okay, because B, you consider B as a harder problem, okay, than A, or at least as hard as A. So if harder problem is already solvable, then the easier problem is also solvable, which is the second way to look at it. Okay? B is at least as hard as A. Okay, so this polynomial time reduction, you can look at it both ways. Okay, and we're going to use the second one. Okay? We're going to use the second one. Okay, going to use the second one to prove the NP complete. Okay, all right. So now, how do we do it? Okay, okay. So now this is the definition. This is the definition of NP complete. Remember, we said NP complete is a problem inside NP that is the hardest. Remember earlier we said that, right? NP complete problem is the NP problem that is hardest. Okay, so when we say B is NP complete, then B must be in NP, right? Okay, it's the hardest problem in NP, right? Okay, so B must be in NP. Okay, and also we said that for all the problem in NP, okay, all the problem A in NP, A must be polynomial time reducible to B. Okay, remember in the previous slide we said A is polynomial time reducible to B. Okay, what does that mean? What does that mean? It means that B is at least as hard as A, right? Remember this is the second bullet. It shows B is at least as hard as A, right? Okay, so if we can prove that for all the problem in NP, okay, all the problem in NP, A is polynomial time reducible to B. That means B is at least as hard as A. Okay, then B is the hardest, right? Because B is as hard as all the problems, right? Okay, so this is the formal definition. This is the formal definition of NP complete. Okay, to define what do we mean by hardest in NP. Okay, okay, so it means all the problem in NP must be polynomial time reducible to B. Okay, so this is the formal definition. Okay, so when you prove a problem to be NP complete, you need to prove this. Okay, if you're given a proof, if you're given a problem B, you want to prove this is NP complete problem, meaning this is the hardest problem in NP. Okay, first of all, you need to prove that this B is in NP, meaning it's polynomial time verifiable. Okay, I give you a guess of the solution. You can verify that guess of the solution is a correct guess or it's a wrong guess. Okay, all right, so that's a polynomial time verifiable. The second thing you need to prove is that for all the problem in NP, the problem in NP can be polynomial time reducible to B, right? Meaning B is at least as hard as A. Okay, so how do we show that for all the NP problem can be reduced to B, right? Okay, so that's the next question, right? How do you prove that all the problem in NP are polynomial time reducible to an NP complete problem, right? Okay, so now this famous guy called Cook, okay, Cook theorem, okay, was published in 1971, okay. Cook published his result, okay, first, and it was also validated that at the same time there is another person called Levin. This guy also proved the similar result independently at the same time. That's why this theorem is called Cook-Levin theorem. Okay, so they prove that the circuit satisfiability problem is an NP-complete problem. Okay, so this in 17.1, this is the first ever problem. Okay, first ever problem that is proved, okay, to be an NP-complete problem. Okay, it's the first NP-complete problem. Okay, this is proved by these two people independent, but most people just say Cook theorem. Okay, simply because I think he probably published a little earlier. So he becomes the first one. Right? Now, most people just mention Cook theorem. Okay, so when people ask you what is a Cook theorem, okay, you should at least say that Cook's theorem, okay, is related to NP-complete. Okay, the correct answer is Cook's theorem proves that the first NP-complete problem, the circuit satisfiability problem, is NP-complete. Okay, all right. So and then in 1 year later, okay, Richard Karp in Berkeley. Okay, so he proved many other problems that are also NP-complete. Okay, but the hardest one is the first. Okay, the first one. Okay, so what is the circuit satisfiability problem? The circuit satisfiability problem is this. Okay, you are given a circuit that consists of AND gates, OR gates, AND gates, OR gates, and NOT gates, and so on, right? All these Boolean gates, they are connected. They are connected together like this, as an example. Okay, suppose this you have N inputs. Okay, you have N inputs and single output. Okay, so in this example, there are 3 inputs. Okay, the question is, I give you such a Boolean network, okay, with N inputs. Can you find a way to assign the input, okay, assign the N inputs to be either 0 or 1, such that the resultant output is equal to 1? Okay, that's called circuit satisfiability problem. Okay, so in this example, if you make this input 1, right, AND gate, so this output is 1. Now this input 0, so NOT of 0 is 1. So 1 and 1 goes through the OR gate is also 1. So 1, 1, 0 is an assignment that can make the output equal to 1. Okay, so the circuit satisfiability problem is I give you a Boolean circuit consists of AND gate, OR gate, and NOT gates with N inputs. Okay, how are you able to assign this N input to be 0 or 1 such that the output is equal to 1? Okay, so in this example, this circuit is satisfiable because you can find this assignment to make the output equal to 1. Okay, as you can see that you can try all combination. This to be 0, 1, 0, 1, 0, 1. They are totally N input. So there are totally 2 to the N possible assignments that you can try. You can try to find the answer. Okay, but can you do better than that? Right. So that's the problem. Okay, so Cook theorem, right? Cook's theorem, he proved that this C satisfiability problem is the NP. Okay, remember, proof NP complete, there are 2 steps. One is to prove the problem is in NP, meaning this problem must be satisfiable. Must be a polynomial time verifiable, right? NP means polynomial time verifiable, right? So I give you an assignment. I just tell you, okay, this input is 0, that input is 1, and so on. I give you an assignment. You can quickly take that assignment to verify if the output is equal to 1, right? This can be done easily, right? by going through this circuit, okay, from the input all the way to output to decide the output is equal to 1. So that means the C set problem, right, circuit satisfiability problem, is polynomial time verifiable, okay, therefore it's in NP, okay. Now the next problem is to prove all the problem in NP, all the problem in NP are polynomial time reducible to C set, okay, and this is where the Cook contribution is. He was able to prove that this is true, okay, and the proof can go through many pages, okay, so we're not going to go through that. We will just take that as a fact, okay, that CSAT is proof to be NP complete. Cook spent many pages to prove that, okay. If you're interested, okay, you can go to the textbook and read it, okay. Okay, so now, given that we have understood, okay, we have understood that circuit satisfiability problem is the first NP complete problem, okay? But how about other problems? How do we prove other problems are NP complete? Should we go through Cook's theorem for every NP complete problem to prove they are NP complete? Okay, the answer is no. You don't have to do that. You don't have to do that with so much effort. Okay, there is a better way of doing it. Okay, it's based on the following theorem. Okay, this theorem is based on that the polynomial time reduction are transitive. Okay, okay. So this is the following theorem. If C is polynomial time verifiable and B is NP complete, okay, C is in NP and B is NP complete, okay, then if we can prove if NP complete problem B is polynomial time reducible to a problem in NP C, right? Okay, then you can claim C is also NP complete. Okay, so this is the theorem. It's a very important problem. Very important theorem. Okay, to prove a problem C is NP complete. Okay, you're given a problem in NP C and the known NP complete problem. If you can show that you can polynomial time reduce B to C, then you can say C is also NP complete. Okay, how? Why is that? Okay, first of all, to prove a problem is NP complete, you need to show C is in NP. That's given. The second one is you need to show all the problem in NP are polynomial time reducible to C, right? Okay, how do you prove that? Okay, it's easy because you see this. B is NP complete. Okay, we know that, right? As given. Okay, therefore, for all the problem in NP, A can be reduced to B. Okay, now if B is also reducible to C, okay, then for all the problem in A can be polynomial time reducible to C. Okay, that means this is the what? That means C, right? C is at least as hard as all the NP problem, right? Right? Okay, so that gives you the proof. C must be NP complete as well, right? All the problem, remember, all the problem in NP can be reduced to C, then C is NP complete, right? Okay, so now given this fact, given this theorem, okay, you need to know, how do you show a problem? How do you show a problem is NP complete? Okay, how do you show a problem is NP complete? First, you show C, okay, problem C is in NP, okay? You are given a problem C, you want to prove C is NP complete. The first thing to prove is to prove C is in NP, okay, meaning it's polynomial time verifiable. The second step is to prove, right? Is to prove you can reduce a non-NP complete problem to C, okay? Like in this case, if B is already NP complete, and you can prove NP complete is polynomial time reducible to C, then C is NP complete. So this is the recipe, okay? This is also Richard Karp, okay? Richard Karp used this two steps to prove many other problems are NP-complete. Okay? Yeah.
Is the second step in this?
Can you speak louder? Can you get closer?
Yeah, the second step in the previous slide.
Yes.
Is the other way around is also possible because?
No, the other way around. No, this is exactly okay. So you ask a very good question. You need to be very clear. Okay, you have to reduce a known NP-complete problem to C. The other way around is the standard mistake that people will make. Okay, please don't make that mistake in the exam. Okay, when you prove a problem to be NP-complete, you prove the problem is in NP. You also prove a non-NP-complete problem is reducible to C. Okay, you see, because you need this. Okay, this is a non-NP-complete problem. Okay, is reducible to C. Then you can say, because B is a non-NP-complete, so A is polynomial time reducible to B. And if B is polynomial time reducible to C, therefore A is polynomial time reducible to C. Okay? Okay, so you need to be very clear. The other way around, okay, is not going to give you the NP completeness. Okay, so don't make that mistake. This has to be the direction from a non-NP complete problem to the problem that you want to prove, NP completeness. Okay? Are you okay?
Yes, I'm okay. Thank you.
Okay, this is very important. Okay, I thank you that you asked this question. Okay, and I'm definitely going to test you that in the exam. Okay, so that's actually the key of the NP complete theorem. Okay, and there are several known NP complete problems. Okay, so so these are so for instance this one. Given the graph, is there a simple path of length greater than or equal to k? So I give you a graph like that. Okay, of 5 vertices. Can you find a path with exactly 5 vertices? Okay, this is called Hamiltonian path problem. Hamiltonian path problem is an NP-complete problem. Okay, all right. So I'm going to stop here. Okay, and this will be our coverage of the final exam. Okay, will be on the slide number 19. Okay, maybe slide 20 is fine. So this is the most famous textbook to talk about NP completeness. It's called Gary and Johnson's book. Okay, this book is a Bible level textbook, talks about NP complete problems. Okay, all right. So we're going to stop at the slide 20. Okay. Okay, now that's it, and I'm going to publish the question exercises you need to practice at home and so on, and that will be it for 580. Any question? We're going to skip the remaining example. These are just examples to show you how to prove the NP complete and so on. Okay, and I think this will be good enough. Okay, to the slide 20. Okay. So if you want to have a summary of this lecture, okay, you need to understand how to prove a problem to be NP complete. If you can understand how to answer that question, you're set. Okay, you're set with this lecture. Okay, how to prove a problem to be NP complete. That's all you need to learn. Okay, in this 20 slides. Okay. Okay. All right, so I just want to thank everybody for your hard working, but we still have the final exam, right? So let's keep up the momentum, okay? And send me questions that you have, and we can also set up time if you need to answer your question, right? But I will try to answer through emails and maybe through phone call and so on, okay, as much as possible. Otherwise, we can schedule to meet and so on. Okay, so otherwise, any question?
Professor, right now we have 29. Do we need any attendance related stuff? Do you need, or
29? What do
Yeah.
you mean? Sorry?
all the who joined to the meeting, the number of people is 29.
Oh, there's 29?
Yeah,
Okay. Okay. Yeah, I
including
think,
you.
yeah, I can, how should I 29. I think that should be good enough.
Okay.
Yeah. Yeah.
And
Okay.
I also made the recording. Do you mind to put it in the public in YouTube and share the link in case some?
Why don't you send it to me, and I'll make an announcement in the ITU Max.
Yeah, I'm gonna put in the YouTube, the public, and then send you the
Okay,
link.
yeah, and then you send me the link. Okay.
Okay, awesome.
Okay,
Okay.
sounds good.
Okay.
Okay.
And I'm going to stop the sharing now then.